to be, we're going to be looking at one-sided limits and two-sided limits today, but infinite limits, basically you can have a function like, let's say I'm looking at the limit as x goes to 2 from the negative direction of 3 over x minus 2. Now, I say infinite limits, we're actually going to use the words infinity or the symbols infinity and negative infinity to describe the limit of a function today, to describe where the y value of a function is going as x moves to a certain number. And typically, going to infinity is unbounded behavior, okay? So visually, a picture like this in the past, if I was asking you what would be the limit as x goes to 0 here, what would be the limit as x goes to 0 of this function? It does not exist, and the reason would be one of two reasons, is that the limits from the left, as x is going to 0, the y value is going down to negative infinity, and as it goes to 0 from above, it's going to positive infinity. So two different limits, but unbounded behavior. Unbounded means shooting up to infinity or shooting down to negative infinity. And if it were just the limit as x goes to 0, then I would describe it as does not exist. But there's something different that we like to do when we're talking about, say, the limit as x goes to 0 from the negative of this same visual function, and the limit as x goes to 0 from the positive. Rather than saying does not exist, we would like to, on the one-sided limits, give a description of where it's going. Okay, we know the limit here does not exist, but the limit as x goes to 0 from the negative, this is from the negative over here, where is the y value going? Negative infinity. So the answer to the limit as x goes to 0 from the negative is negative infinity. Does not exist. Okay, one-sided limits always have an answer. The answer may be negative infinity or positive infinity, but you never give does not exist for a one-sided limit. Okay, so the limit as x goes to 0 from the positive. Here's x going to 0 from the positive. Where is the y value going? Positive infinity. So one-sided limits should always get an answer, whether it's a number that you got using normal substitution. That's what you always hope for. You hope to be able to plug a number in and get the answer out, right? Don't you? That's the way I want it to work. If it doesn't, then I might try some algebra, but a lot of times there's not algebra to do. So then we're probably just going to have to do some numerical limits. Okay? But this example, we need an answer. And it can't be does not exist. So the first thing I am going to do is I'm just going to try plugging 2 in. Okay, so when I plug 2 in, what do I get on the top and on the bottom? Okay, now, is this indeterminate form? It's really not, because you should have 0 over 0 to be indeterminate form. So, and again, we have a one-sided limit, so we need to provide an answer. We can't just say does not exist, okay? Our calculator can't do this. So this is still an indeterminate form, kind of. But what it should tell us is that if we get a number divided by 0, it is probably telling us that our answer is going to be either negative infinity or positive infinity. That's what it's telling us most likely with the one-sided limit. Okay, this is basically saying as x goes to 2, this graph has probably got this type of unbounded behavior. And so really the best and easiest and fastest way to find it, because guess what? There's no algebra you can do to 3 over x minus 2. There's nothing you can do to this to simplify it and make it so that you can just plug 2 in. Not going to happen. So what I'm going to do is I'm going to pick numbers that are going to 2 from the negative. I'm only going to pick 2 of them, and I'm going to plug those in. And I basically do a little numerical integration. Okay, so I'm going to plug Okay, these numbers need to go to 2 from the negative. So what numbers are really close to 2 but below it? Okay, 1.9 and then 1.99. And I need to plug those x values into my function. Is this a pain? No, it's really not that bad. Okay? Do I expect you to show work? You know, like work it out by hand? No, I don't. So for this, I'm going to take and plug 1.9 in for x. So I'm going to have 3 divided by, I better begin the parentheses, 1.9 minus 2 end parentheses. Calculate it, I get negative 30. Okay, so can you guess which of these answers it's going to be? It's probably negative infinity. How do you know? Because that's negative. Let's just double check. If it's actually going to negative infinity, what should it happen when I plug a number in here? Should it get, it'll get smaller, like negative whatever, 90 would be an example, okay? So maybe, yeah. So now I'm going to type in 3 divided by, begin parentheses, 1.99 minus 2, end parentheses, and that's negative 300. Yeah, it did get a whole lot smaller. So what would be the limit as x goes to 2 from the negative of that whole thing? It would be negative infinity. Okay? That really is going to be the easiest way for you to find the limits. Could you have graphed the function? Could you have graphed the function and use the graph? Okay, yes, I will only give you credit if you provide the graph on your paper. Or do this. You don't have to do both. I don't need you to solve things 15 different ways. One way is fine. Okay, this section here, you know, we're adding a new thing saying, okay, one-sided limits always need answers. And those answers can be negative infinity or positive infinity. But really what we're saying is you can utilize all of the methods that we've talked about so far for finding limits. Numerical tables, looking at graphs, using algebra, substitution. Okay, those are really all the ways we have of finding limits. Trig limits, the sine of x over x. 1 minus the cosine of x over x. Those are known limits. All right, so now that's finding one-sided limits. Okay, what if I gave you a problem like the limit as x goes to negative 3 of 1 over x squared minus 9. What's the first thing you're going to try to find that limit? Plug in negative 3, okay? And what do you get? You get 1 over 0, okay? So now what should you do? Is factoring the bottom going to benefit you in any way? Why not? Nothing will cancel, so I'm not going to factor. Algebra isn't going to help me here. Remember what I said? You get something like 1 over 0. Is that like 0 over 0 indeterminate form? No, 0 over 0 indeterminate form is the one that says you can probably do algebra. But like 3 over 0, 1 over 0, no, probably no algebra. Your answer is probably going to be what? Negative infinity, or in this case, is this a one-sided limit? No. Or this one, can this have a DNE for an answer? Yes, it can. So, I mean, to me, I might just want to look at the graph. So that graph is going to be 1 divided by, begin parentheses, x squared minus 9, end parentheses, graph that. think I did. There we go. Okay, do you see that spot right there? That x value is what? That's -3. So the proof that I would write here, I would, sketch the graph. Here's -1, 2, 3. And it looks like this. I mean, that's the whole graph. So what would you say that limit is as x goes to -3? Does not exist. Okay? So this limit does not exist. Why wouldn't it be positive or negative infinity? It's not one-sided. What if it was the limit from the negative? What would be the limit as x goes to -3 from the negative? That would be positive infinity because it's shooting up. Okay, and from the positive, negative infinity. Okay, so all we're doing is throwing in, you got to be fully aware of the limit that you're finding here today. Is it one-sided? Is it two-sided? Okay, one-sided limits need an answer. Two-sided limits can be, does not exist, but just because we're doing a section on limits at infinity doesn't mean every two-sided limit is going to be DNE. Don't try to make rules like that. Okay? All right, so the next thing that we need to talk about here is what's called vertical asymptotes. Okay, vertical asymptotes and holes. And we've actually already done kind of a little bit on this, but you're going to be given a problem. Oh, I don't know, like find the vertical asymptotes of so find all the vertical asymptotes for f of x equals x squared plus 1 over x squared minus 9. Find all the vertical asymptotes. And find all of the vertical asymptotes for f of x equals the cotangent of x. All right, so vertical asymptotes. This function has vertical asymptotes. Vertical asymptotes are those lines at x equals -3 and x equals 3 where the function has unbounded behavior. Asymptotes happen at x, it's like numbers that aren't in the domain. Okay? If it's not in the domain, you may or may not have an asymptote. X values that aren't in the domain can create asymptotes where the function is not defined. Also where the function is not continuous. Those are all places you can have vertical asymptotes. And these are really easy to find. In a rational function, the vertical asymptotes will be where the bottom is equal to 0. The vertical asymptotes will be where the bottom is equal to 0. Okay, so I set the bottom equal to 0. How am I going to solve that? I'm going to factor it and solve it. So my vertical asymptotes will be at x equals 3 and x equals -3. Okay, now, occasionally, these are not both vertical asymptotes. Okay? They are not vertical asymptotes and become holes if the top will also factor and then you can cancel one of those parentheses. So does the top factor? This doesn't factor. This is not a difference of squares. It is a sum of squares which only factors in an imaginary way. So in other words, it doesn't factor. Okay, so even if it could, yeah, it doesn't factor. Does not factor. So are you going to be able to cancel either of these? Remember when we did that removable, not removable discontinuities? That's really all this is. We're just, the non-removable ones are vertical